Okay, so this is, oh, I should mention this is now section 4.6. So these are applications of, well, exponentials and logarithms. So these are the word problems, right? This is, if you want to know what's the point of logarithms, what's the point of exponentials, well, it's to solve problems like this, right? So actually, before we do this example here, we should mention that when you put your money in a bank, you get compound interest, right? In other words, they compound the interest every day usually. But it could be compounded any number of times a year, right? So let's start with P dollars. This is sometimes called the principal or present value. Principal or present value. It's the amount you start with, right? A is the amount you have at any given time. So this is the amount at time t. T, of course, is, well, for these problems, I'd say it's the number of years, but in other problems, it could be any amount of time, right? But for compound interest problems, it's always going to be in years, and the reason for that is because the interest rate, R, is the annual interest rate. It's 5% per year, right? So this is the interest rate as a decimal, not as a percent, right? You got to write it as a decimal. And n is the number of times you compound, number of compounding periods per year. Right? How many times are we compounding per year? Is it quarterly? Right? Quarterly means n equals 4. Are we compounding monthly? Right? That would be 12 months in a year. Are we compounding daily? Daily would be 365. That's how many days in a year, right? And if you compound once a year, then it's just n equals 1, right? So the formula for compound interest, the amount of money after t years, so thinking about this as a function of t, is P times 1 plus R over N raised to the NT. I don't remember if we did this in 4.3. I think we did. But here's a reminder then. Here's a good reminder, right? Okay. Now this is if you're compounding n times a year. What if you're compounding continuously? So this is n times per year. Right. On the other hand, if you're compounding continuously, you use a different formula, right? You use the Pert formula. A is equal to P times e to the RT. And again, we're usually thinking about this as a function of t, right? So P e to the RT is when you're compounding continuously. And this is if you're compounding discretely, n times a year. Okay. All right, so now I think we can get to example 1 here. And I know I'm going to run out of space quickly, but I'll try to squeeze it in here. Example 1. I hope I made this big enough, but I'll read it again. Suppose $6,200 is invested at 3.5% compounded continuously. Part A is we want to find the amount of money after 10 years. So how much money do we have after t equals 10 years? Right. Oh, before we plug in 10, of course, let's get the formula, right? Notice we are compounding continuously here. Right? The key word here is continuously, and that means we're using the Pert formula, so let's write that down. A is equal to P, well, A of t, right? A of t is equal to P times e to the RT. Okay. Now let's plug in the numbers, right? In fact, before we plug in the 10 for t, P is going to be 6,200. Right, because that's what we're starting with. That's our original investment. Maybe I can write that down. So P is 6,200, right? R is not 3.5, it's 0.035, right? 0.035 as a decimal, right? So be careful. If you use R equals 3.5, that's actually 350%, and you're never going to get that. Unless you're a really good investor, maybe, but not from a savings account in a bank. In fact, you're lucky to get 1% these days. So yeah, don't forget to convert to a decimal. It's 0.035. Oh, times t. Right? But in this case, t is 10. So plug in t equals 10. You get 6,200 times e to the 0.035 times 10, which is actually, so 6,200 times e to the power 0.35. Okay. And in fact, that's how much money you have after 10 years. But what is that exactly? I mean, what is that approximately, right? Use your calculator. So give me a second. I got to do this. Okay, well, again, some of you are going to have trouble with your calculator. If you have a TI 84, 83, a regular graphing calculator, you can put this in exactly as it says, right? You do 6,200 times, and you don't even need the times here, e to the power, so you use the little caret here, but on your calculator it probably does this, and just hit enter, right? Now, if you have a scientific calculator, you might have to calculate this first. So this is 6,200 approximately times 1.4190675 blah, blah, blah. All right, so it's that. And then when you multiply by 6,200, you get 8,000, and this is going to be in this is going to be in dollars now, $8,798.22. You could put in 21 cents, but you should round up to 22 cents. So, right, you start with $6,200, and after 10 years, well, just due to interest alone, you get an extra 2,500 something, almost $2,600, I think, right? But yes, you have $8,798.22 after 10 years, which is a long time to wait, of course. I mean, you know, remember, this is only 3.5%, and you got to wait 10 years to get that much more. So that's the idea here, right? Now, there was a part B, so let me see if I can remember. Part B is how many years will it take for the investment to reach $10,000? Okay, so now we want $10,000, right? So how long do we have to wait now to get to $10,000? Well, we know it's more than 10 years, right? Because in 10 years, we don't even have $9,000 yet. So you could guess maybe 20 years or maybe 15 years or something like that. But we want to know more exactly how many years. So, you know, we'll round to the nearest, I don't know, maybe 1/10 of a year. Is that all right? Yeah, it doesn't say, but let's do 1/10 of a year. Okay, so now for part B, we got to do this problem here. Part B. So here, we don't know what t is, right? We're looking for t. But we know P is still 6,200. This is still E. This is still 0.035. 0.035 times T. And we know that has to be 10,000 because that's what we want to end up with, right? So now we have to solve for T. And this is something we did in the previous video in section 4.5, right? We were solving exponential equations, right? There's no log here. It's an exponential equation. T is in the exponents. Okay, so how do we solve for T? Well, you can take the log, but before you do that, notice this is times. I would divide both sides by the 6,200 first. While you don't have to, I think that makes the most sense here. So when you cancel the 6,200s, the left side is just e to the 0.035t. And on the right side, well, we're going to have to approximate eventually, right? This is 100 over 62, 50 over 31. Oh, okay. Right, so it's 50 over 31. But we can approximate that. Just use your calculators. 1. And I think we get 1.6129. Okay, and that's to 4 decimal places, and that should be enough, right? So what do we get now? We get this equation. And I'm writing equals, but remember this is approximate, right? Or if you don't mind, I could just write the 50 over 31. Yeah, I'd rather do that for now. Right, so you have your a to the m equals n. Now I think I wrote it backwards, right? A to the n equals m. I can never remember. No, I think this is right. I think this is right. So you know what to do with that, right? M is just log base a of n. Convert to a logarithm. But because I'm running out of space here, let me go way down. So here's the equation one last time. And when we convert to a logarithm, we get 0.035 times t equals log base e of 50 over 31. All right? Which, remember, log base e is natural log, ln. So you can just do that on your calculator, right? So we have 0.035 t is equal to the natural log of 50 over 31, which is approximately 0.478036. So now just divide by the 0.035. Right, and that tells you what t is. So let me write down the exact answer, right? The exact answer is natural log of 50 over 31, that's a 3 there, 31, divided by 0.035. But as a practical matter, right, that tells you how many years you have to wait to reach $10,000. So how many years is this, right? Is it 12 years? Is it 14 years? Is it 20 years? Right, so this is where we use a calculator to approximate. So I think I did that. Just divide by the 0.035, and I get approximately, oops, sorry. Let's try that again here. This thing. Sorry about that. All right. You get 13.658 years. And what do we say? The nearest tenth of a year, so 13.7 years. Right. So it was somewhere between 13 and 14 years. Yep. Which is more than 10 years, right? We already knew that it was more than 10 years because after 10 years, you only get about just under 9,000. So you got to wait another 3.5, almost 4 years to get to $10,000, right? But that's it. So that's part B. And part C, how many years will it take for the investment to double? So, right, so part C, how long to double? The original investment. The original investment, if you remember, was $6,200. So what's double that? It's $12,400. So that's what we want to solve for now, right? So we still have, 6,200 times e to the 0.035 t, but instead of 10,000, we now want $12,400. Okay, so now we're solving this equation, done exactly the same way, right? The first step is to divide by the 6,200. Right. Cancel those. And now we're left with e to the 0.035 times t equals, well, 2, right? You get exactly 2 here. Okay, so once again, we know what to do here. We convert to a logarithm. The other thing you could do, of course, is take the log of both sides. As long as it's the same base on both sides, I would use base e. If you take the log of base e on both sides, you end up with the same thing. Right. So just divide by the 0.035 again. And there's your t. So again, the exact answer is the natural log of 2 divided by 0.035. That's a 5. And then the approximate answer, again, just use your calculator. I get about 19.8 years. Okay, so almost 20 years for your money to double. Well, assuming that the interest rate is 3.5%, yeah, the interest rate is 3.5%, and we're compounding continuously. That means we're compounding every moment in time, right? Which seems unusual, but that's what continuously means. You're compounding all the time, as opposed to compounding just once a day or once a month or something like that. So I hope that helps. Okay, one more. So this is the amount of sodium-24. It's an isotope of sodium in grams. T hours from now is given by this formula. And maybe I'll copy down the formula if it's too small. So the formula that they write, so this is given. Oops, hang on. Sorry about that. So this is given that A is equal to 94.2 times e to the negative 0.046333t. So don't ask where this comes from. This is the given formula for the amount of sodium-24 after t years. Okay, so that's given. So the first question is how much sodium-24 is there now? Well, right, so how much do we have now? Well, right now, of course, is 0. 0 years later is right now. So they just want us to plug in t equals 0. So if t is 0, we get 94.2 e to this awful number, 0.046333, times 0. But anything times 0 is 0, so you get 94.2 times e to the 0. Right. So hopefully you remember that e to the 0, or anything to the 0, is 1. So you get 94.2 times 1, which is 94.2. So that's where this number comes from. It's how much you have right now. Very similar to the last problem where that told you how much money you have at the start of your account, right? So yeah, this is in grams, so don't forget to put the units. This is grams, 94.2 grams. That's how much we have right now. Part B, how much will there be 24 hours from now? Oh, I'm sorry, did I say years? I meant, right, so t is in hours here, not years anymore. T is in hours. Okay, they state that right here in the problem, right? So t is the number of hours from right now. Okay, so 24 hours from now is t equals 24. So be careful you don't do t equals 1. You might think, well, that's 1 day. Yes, but the t is in hours, so 24 hours, right? Okay, so you do the same expression. This is 94.2 times e to the negative 10, negative 0.046333 times 24. And yeah, just stick this in your calculator. And you should get, well, let's see. You get 94.2 times the exponential part is 0.3289. So when you multiply by 94.2, you should get 30.98. Well, when you round to the nearest tenth actually gives you 31.0 grams. You can abbreviate G for grams here. Right, so 24 hours from now, there's only 31 grams. So what happened? Where did it all go? Because we started with 94.2 grams. 1 day later, there's only 31.0. So again, I wouldn't worry about this. This is a physics problem. But sodium-24, I think it's Na24, is it's a radioactive isotope of sodium, of salts. And unlike, sodium, not salt. Salt is sodium chloride. This is just sodium by itself, right? So this isotope of sodium is radioactive, which means you got, radiation coming from it. And that radiation, those are particles, and those particles have mass. So as it radiates, it's losing mass, right? So that's where it went. It basically is, particles, electrons and helium nuclei that fly off of it. But again, it's not, you don't have to worry about where it went. Just know that this is how much you have left after 24 hours. Right. So part C, question there is, what is the half-life of sodium-24? So I don't think we've seen this word before, half-life. I mean, I know it's a video game, but that's not what this is referring to. The half-life is the amount of time, in this case the number of hours, or days or years, the amount of time to reduce to half the original amount. Okay, so we're starting with 94.2 grams, right? 94.2 grams. What's half of that? You get 47.1. 47.1 grams. So we want to know how long it takes to reduce to this amount, right? So here's the equation you're looking for, right? So A is the amount. We have 94.2 times e to the negative 0.046333. If you're wondering, should I round that at all? I wouldn't, but if you don't round it to, say negative 0.05, maybe just lop off one or two of the threes, you'll be fine. But in general, you shouldn't round. Right? Even though we're rounding this to the nearest tenth, in some cases you might want to be more precise. Anyways, we want this to equal 47.1 grams. So, right, first step is to divide by 94.2 on both sides. Right, cancel these, and of course this should be 1/2. That's for the half-life. Right. So the left side is, let's see, e to the negative, same number, 0.046333, times t, that's what we're looking for, t, is equal to 1/2. So you solve that the usual way, right? Convert to a logarithm. Oh, I'll write it down one last time, right? A to the m equals n means m is equal to log base a of n. Right. Again, at some point you really should know this, because if you don't know this, you're either going to have to look it up, and that could take a lot of time, right? Or you're going to run into a lot of trouble here, because it's the only way I know how to solve this is to use this. Or take the log of both sides, but it's the same idea. It's the same principle. So negative 0.046333 times t is equal to the natural log, right? Log base e is natural log of 1/2. And natural log of 1/2, I know, is about negative 0.693. So when you divide by this negative number, it's a negative divided by a negative. Oops. Sorry, that's supposed to be a 6, not an 8. So plug that on your calculator, and you should get approximately 14.9569. So say 14.96 years. Oh, sorry, not years. This was in hours, right? This is in hours. Yep. So slightly under 15 hours. In fact, again, did they say how far to round? No. So, you can round up 15 hours, I guess. Just read the question carefully. They will specify how far to round. And if they don't, then just round as much as you want. I would generally keep at least 2 decimal places, but here it's what is this? 14 hours and, 58 minutes, 59 minutes. Not a big deal, right? So 15 hours, right? So, which makes sense because after 24 hours, we're down to 31 grams. So to be down to 47 grams doesn't take quite as long. Right. And finally, when will there be 5 grams remaining? So for 5 grams, the amount, right, is still 94.2 e to the negative 0.00, nope, not 0.004633 times t. When will there be 5 grams? So just let that equal 5. And you do the same thing, right? Divide by 94.2. And what are we left with now? We get e to the negative 0.046333. I'm not going to round. Is equal to, so 5 divided by 94.2 is approximately, oops, there we go again, 0.05307879787885. Doesn't matter because we're going to approximate anyways. Yep, I think that's right. So take the log of both sides, and you get this. Again, this will be approximate, but that's good enough. And I get negative 2.93598. So when you divide, I get that t is about 63.3 hours, right? Not years anymore. 63.3 hours. Okay. Well, I hope that helps. So again, some problems are going to involve exponents, and if you want to solve for the exponent, you need to take a logarithm, right? In other words, you need this. Right? In this case, we're going right to left, but in some cases, you're going left to right. Right? That's if you already have a logarithm, and you want to get rid of the logarithm, you convert to an exponential. All right, so how about one more? Okay, so we have a town's population grew from 6,140 people in 2005 to 7,435 people in 2015. Part A, what is the growth rate? So for part A, we just want the growth rate. So what do they mean by growth rate? Well, right, since you're growing, how fast are we growing? Right, so by how many, not how many people a year, by what percentage rate per year? right? So the growth rate we'll call R for rate, right? And since it's growing exponentially, oh, they didn't say that, but it would say that in the problem, right? Right, we're assuming exponential growth. Exponential growth. Right. So in other words, the population at time t, right, and this t will be in years in this case, right, because, well, it's 10 years later, right? So the original population was 6,140. That's a 0, right? Oh, gosh, that's a 0. Times e to the power r times t, right? Where r is the growth rate, right, per year, and then t is the number of years. Okay. So what do we do? Well, the population, we know 10 years later, 10 years after 2005, that means 2015. Right? So t is 10 here. This is r times 10 in the exponent. Well, we know the population was 7,435. So we're solving for r, right? This time we want the growth rate. It's done the same way, right? Divide by the 6140 on both sides. Boom, these cancel. And so we're left with, on the left side, just e to the r times 10, or 10 times r, same thing. And again, you need a calculator to do this, because I'm not going to leave it exact here. So 7,435 divided by 6,140. And again, don't round too much, right? Hang on, if you put, this pen here is driving me crazy. I know it's a stylus, not a pen, but it's, all right, 1.21. I would do a little more than that. How about 1.2109? Okay. I mean, obviously it's not that big a deal, but you don't want to round too far here. That's the key. Right. So now convert to a logarithm, right? So 10 times r is going to be log base e, which is ln, right, of 1.2109. Okay, so I hope you're used to that by now. Right, so now we just divide by 10 on both sides. So my r is natural log of 1.2109, all divided by 10. Right, so what do we get? I get 0. Oh, there it goes again. 0.019. Do we need another one? Yeah, okay. Right. So 0.0191, let's say, right? As a percentage, of course, the growth rate, if you multiply by 100, the growth rate is 1.91%. So I think that's what they're looking for. So about 1.91%. All right, part B. What will be the population in the year 2022? So it's only a couple of years away, but 2022. So what's the population going to be then? According to this model, it should say according to this exponential growth model here. Okay, so for part B, there we go. Part B, we want the population in 2022. So be careful. That's not my t. My t is the number of years, right? So t, number of years since 2005, right? See, that's why I plugged in 10 here, because 2015 is 10 years later, right? 10 years after 2005. So, right, so my t, 2022 minus 2005, that's 17 years later, right? So my t is 17. Well, that's not the answer. That tells me what to plug in, right? So here's my model here, right? So p as a function of time is 6140 times e to the power r, which is 0.0191 times t. But now, if we want the population 17 years after 2005, that's 2022, we just plug that into the exponent. Right. And then plug it all in your calculator. And if we did this correctly, we should get 8,495 points, right, 399, so 0.4. But hang on, what are we talking about here? We're talking about the number of people. So there is no 0.4 people. We'll just round to the nearest whole number. So how many people will there be approximately in the year 2022? About 8,495 people. So that will be the population, right, in the year 2022. 2022. Okay. Which I think that makes sense, right? Because in 2015 there were only 7,000 people, so this is growing, right? And finally, part C, when will the population reach 10,000? So we want the population at time t. This is still let me use a different color here for part C. I should be color coding these, right? Okay, so here's the equation again, 6140 e to the 0.0191 t. We don't know what t is here, right? We're solving for t because we want 10,000 people. We want 10,000 people. And so, so how long is that going to take, right? Well, we know it's going to be after 2022 because in 2022, we only have 8,500 people or so. So it's going to be a lot longer than 17 years, right? Let's see. So divide by the 6140, and you get e to the 0.0191 times t equals 1.6286. 1.62, should I round to 629? Probably good enough, right? 1.629, I think. Actually, well, okay. Now I might be a little bit off here, but fair enough. 1.63 would be good too, but now see, if you only round to say 1.6, you're going to get, your answer is going to be quite different than what it should be. You're going to get something called round-off error. So if you round too much, you're going to get round-off error. And so you might be off by, years, right? If we rounded, for example, this to only 0.02, we might have gotten, 8,600 people or 8,200 something people, right? So you might be off by, not just tens of people, you might be off by hundreds of people if you really round badly, right? If you round too much. Okay, so now converting this to a logarithm, right? The exponent 0.0191 times t is going to be log base e, or natural log, of 1.629, right? And then just divide by the decimal 0.0191. So that gives me a t. Well, okay, so again, here's a more precise answer. Plug that in your calculator, and what do you get? Looks like 25.5 years. 25.5 years. Right. Well, 25.5 years after 2005. So that's going to be, well, in the year 2030. Let's try that again. 2030, right? Okay. So that should answer, right, when will the population reach 10,000? Sometime during the year 2030. And you can say, well, roughly halfway, maybe in June or July or something, but we don't have to be that precise. So in the year 2030, we expect the population to reach 10,000, again, based on this model, based on this exponential growth. So, yeah, 3 good examples, one involving population, one involving radioactive decay, and then the first one I think involved compound interest, right? So, well, okay, I want to mention one last thing. This might be helpful, right? In part A and part C, these were both growth, right? As time goes on, if you were to graph these functions, right, you're getting bigger. Your population's growing, your money is growing because of interests, right? And so you get this exponential graph, right? Something a to the x, right? Or e to the x, if you like. But in part B, that was a different problem because there we started out with some amount of, I believe it was sodium, some radioactive isotope of sodium, and then over the next few hours, that amount decreased, right? So this is what's called exponential decay. This is exponential growth. And the difference was the exponent, right? If you have a growth rate, right, you might have, I believe it was 1.91% growth rate in this problem. And in the previous problem, I forgot what the decimal was. Something like negative 0.046 something. So that was about negative 4.6% growth, right? So roughly every hour that goes by, you're losing about 4.6% of the amount of sodium. That was the previous example, right? In this example here, the one involving population, right? Every year that goes by, the population grows by a little less than 2%. So I hope that helps explains what these R's are. These are the R's in the exponent, right? When you do e to the RT, right? So when you're decaying, R is negative. When you're growing, R is positive. Okay, so I hope this helps.